Ludmila, who will be talking to us about infeasible space reduction for QAOA through encoding-change. So take it away.
Hello, can I share my screen?
Yep, go ahead.
All right, can you guys see it?
Yep, all good.
Okay, so first of all, thanks for introducing me. My name is Ludmila Botelho. I'm a student here in Polish at the Institute of Theoretical and Applied Informatics of the Polish Academy of Science. And well, thanks for this opportunity to giving this talk at such a nice conference. And let's get started. Okay, I don't know about you guys, but historically speaking, this whole idea of quantum algorithms, it brought novelty and excitement since they can provide us significant speed ups in terms of complexity and help us to answer difficult questions like what are the prime factors of a big number, or consider that you need to quickly search for something on a structured database, where is it? So if you think about it, about this particular algorithms, they could be easily solved in big, powerful machines. But what we have today, well, we don't have much qubits available. Quantum machines are noisy, and we are not able to implement exactly unitary gates. And also we have some problems about the noise in the measurements. So does it mean we have to give up about this? Of course not. We just need to come up with another approach. Another paradigm arises from this, which is the noise intermediate scale quantum computer. So what we can do, for instance, there is one of these algorithms worth mentioning is the quantum annealing process. This algorithm is used for solving optimization tasks expressed in the term of a two-local Ising model, Hamiltonian. The Hamiltonian should be designed in such a way that its ground state encapsulates the optimal solution to the considered problem. Optimizing to a two-local Ising model is known to be NPhard problem in a general case. And okay, so quantum annealing has some problems about the devices. So our alternative to this quantum annealing is the quantum approximate optimization algorithm. And in this approach, any continuous time evolution of this form, of this equation here, can be approximate of making use of the Trotter formula. I'm not going to explain all the mathematical details because I think it's out of the scope of this presentation, out of time as well. And anyway, why I'm talking about this? Well, QAOA is suitable for gate-based quantum computers. It can be run on superconducting qubits from IBM or trapped ion machines from IonQ. So, okay. Since we are thinking about optimizing NPhard problems, I think one of the most famous ones of this kind of problems is the traveling salesperson problem, which is given a cost between traveling between cities, we want to find the cheapest route such that the road goes through all the cities and comes back in a closed loop, like in a graph, in the cheapest way, of course. So considering this, and if you guys had paid attention and Adam's presentation before, this kind of problem can be turned in a quadratic unconstrained binary optimization, Hobo model, which is formally defined like this, as you saw in Adam's presentation before. And okay, in a binary form, so it's this b value can be 0 or 1. And this constants here, okay, we can write Hamiltonian in such form where those constants a and b need to be adjusted in such manner that the optimum AQ is the same is at the same time the optimum for the TSP problem. Okay, so what's the problem about this? Well, as we also saw in the Adam's presentation, a lot of stuff I'm doing here is mostly rely on this previous presentation. Well, this requires a number of qubits like n squared are used, and the number of roads it's n factorial. So, but the problem is optimal solution encoded in this case is going to be this logarithm form. And what is going on is actually the overlap between the feasible space and the solution is like, and it's reduced, like the space is increasing in different speeds, let's say. So for instance, like this approximation, like for n square, consider we're going to use n square qubits, like and we want to divide by the feasible space, we have this size, and this optimal encoding is going to be like of this order. So this is kind of problematic. Anyway, what we are proposing here is a new approach, which is called Encoding-Changing quantum approximation optimization algorithm, or just EC-QAOA. And the deal is like it requires in the order of n squared qubits. And also we have to deal with the secret depth. We want to, find a good solution between a number, like a long circuit and a short circuit, what was going to be in between. And also a new feature about this, it's enable errors mitigation. So what about the encodings, right? I'm talking about. Well, we need to calculate, since we're talking about the TSP problem, TSP, we need to figure it out, the cost of road, given some permutation of the roads, like, okay, this matrix is W here, it's just encoding the cost between the traveling from the city 2 to the city 3. So we need to find like a set of permutations that minimize this cost function here. And give it for the city with the time, and this is what we want to minimize. In the previous talk, like we need to encode this information in forms of bits, right? Because we want to make a computation of it. So there is two forms, primary forms, interesting forms to encode this number of the city to, I don't know, some binary or unary, I mean, one hot encoding. And it happens in this form, for instance, that on one hot, it's just, you're just going to put the position of the, I don't know, the city like this, like if we put the 0th city in the first position, the first and the second, and then so on. And the binary is just a binary that we are using. This is interesting because like unary encodings correspond to the QWorld formulation of the TSP, but also why not think about a mixing encoding of the Hamiltonian, mixing like this mixture between one hot and binary to deal with this task? Why not? So this is where the EC-QAOA comes from. Like, let's think about for Hobo encoding. If basically what we have is like a long circuit with not so many qubits. And QWorld, what we have is like it's a short circuit, but it requires a lot of qubits. So what we're doing here is actually something between. For this we initialize, of course. The trick here is initialize the state with a very special state. We have some maximum overlap with the feasible space, and we do most of we did these calculations on basically QSKIT and so on. So initialize the states and applying like this V gate. So from here we start in binary. So we apply this V gates here to go to unary, and then we can apply the QWorld formulation as usual, and then go back with this V dagger here with a map to go from unary to binary, and then we can apply the Hobo mixer, Hobo size mixer. If you want more details about how this gate works, we can provide on our paper. And what's the very interesting feature here is like because is the possibility of using post-selected measurements, so that we can take into account of only feasible solutions, only the interesting solutions here. Note that what we call infeasible solutions are the ones in the sense of the EC-QAOA, not in the sense of the TSP, of course. So in other words, here we consider a measurement of outcome, a feasible one, if the penalty Hamiltonian, that we described before, gives a positive energy to it. If you want more details, I can explain in the question sections. And we can apply the post-selection for the circuit, like in the end of the circuit, or in mid-circuit measurements, like in between measurements. So we can continue the computation only if the ancillaries are correctly assigned everywhere. And what is this interesting? Because the probability of measuring the quantum state on the feasible states increases with this approach. Here we have this graphical informations for the probability of measuring the infeasible space. And we have a comparison between the Hobo QAOA from the previous approach, AC, and the usual QWorld. And as you can see, like the probability for AC is quite good. It's almost compared to the Hobo, which has a good probability of measuring it. And in terms of error mitigation, we made our protocol, we made our analysis assuming that we have 1 qubit and 2 qubits noise gates, and with this values of gamma here for the noise, using amplitude damping noise. And we compared the 3 scenarios using no post-selection, or basically doing nothing with the circuit. Post-selection in the end, like just in the end of the computation, post-selection the answers, and post-selections in the end and between the circuit, like every layer that the algorithm is applied, you can put some post-selection there. And the comparison is going to show you good, nice results, because like with post-selection in the end, we can already, decrease the energy, because, okay, we want to measure the ground state. So we already have a better measurement for the energy. And of course, of post-selection is the ideal scenario. And also for probability in the bottom, we can also achieve very nice results. Like just with post-selection in the end, you already have a significantly difference, okay? So in conclusion, what we were talking about here, what we showed is basically EC-QAOA really works in a smaller space and allows better energy estimation and error mitigation process. And of course, it can be improved in several directions. Well, I guess this is it. Thank you very much for the audience. And if you have questions, it's time.
Okay, thank you, Ludmila, for the nice talk. So does anyone have any questions? We have quite a bit of time. So there's a question in the chat. What is the H mixing gate?
H mixing gate. Okay, let's go back. Okay. H mixing gate is just like, because here we're splitting the Hamiltonians in 2 parts. We have a specific Hamiltonian implemented for QWorld. And this H mixes is a mixer Hamiltonian that comes from the Hobo approach. So like in the QWorld, it's require like, since we're dealing with the one hot encoding, the space for calculating this, the number of qubits is bigger. But the H mix only acting on the non-ancillary state, like non-ancillary qubits. So this is where it comes from. Just like since we can make this mixer approach using a Hamiltonian specific for one hot and a Hamiltonian specific for binary. So that's the difference basically. And we optimize it.
Okay, good. Any other questions? So, okay, I'll ask one. So you mentioned about error mitigation.
Yes.
So could you describe in the kind of specific algorithm? I'm not sure if maybe I just missed it.
Specific kind of algorithm? What do you mean? Like what do you
mean by error mitigation here?
Oh, error mitigation is basically like we can use some post-selection protocols to evaluate it better. Okay.
Right.
And more specifically, okay, some in terms of Qiskit language, we are using some cross gates and stuff like this.
Okay, because so all of this, all of these simulations are still noiseless.
No,
am I correct in assuming that? No. Okay.
No. If you go back here, like you actually in this slide here, I would just say like we just assume that we have for 1 qubit and 2 qubit gates. We are assuming that they are noisy and are affected by amplitude damping kind of noise.
Okay.
This noise model is to be more specific.
All right. Okay, that's good. That's good. Okay. Nice. Okay, so we have maybe time for one or two more questions in case someone wants to get it in. All right. So if not, thank you again, Ludmila, for the very nice talk.
Thank you very much.
Nice to have these two talks from you and Adam as well on this type of work. So thanks again.
Thank you.